Okay, so this is a problem from 2016 comprehensive exam. So this is the question: to prove that a matrix has equal minimal and characteristic polynomial if and only if there is a basis of the form VAV A square V dot dot. And so let's first prove the left to right direction. So suppose the minimal polynomial of A equals to the characteristic polynomial of A. And this means that there is only one invariant factor. Because the last invariant factor should be equal to MA, and the product of the invariant factor should be equal to the characteristic polynomial. And this means that the rational canonical form of A is a companion matrix. Because there's only one invariant factor, then the rational canonical form only have one block, and this is a companion matrix, which of the form like 0, 1, so this is the form of the companion matrix. So A is similar to the companion matrix that's denoted as R. So there exists invertible matrix, let's say P, such that P inverse AP equals to R. So since P is an invertible matrix, then the columns of P should be linearly independent. And actually they form a basis for n by n matrix. So let's say P equals to B1, B. So the column vectors of P denoted by B1, B2 up to Bn, and they are linearly independent. So now let V equals to B1. Then let's investigate what is AV. AV is the first column of AP, and since A is similar to R, then AP equals to PR. Yeah, so this is also the first column of PR. So but the first column of PR, if we investigate the first column of R, then we can see that the first column of PR is just equal to the second column of P, which is B2. Yeah. So similarly, let's investigate A squared B V. Then A squared V is just equal to A times B2. Yeah. And this is the second column of AP, which is the second column of PR. And since the second column of R is like 1 in the third entry, but 0 in the other entries, so the second column of PR is just the third column of P, which is B3. So similarly, we can have A to n minus 1 V, equal to Bn. Yeah. So this set of vectors from v dot dot up to a to n minus 1v equal to b1, b2 up to bn, and which is linearly independent. And since we are in the n-dimensional vector space, so and we have n vectors here, so this is both linearly and it spans the vector space. So this is the basis. Yep, so we've proved the left to right direction. And let's now suppose that there is a basis of this form. Then of course, since they are a basis, since it is a basis, so they should be linearly independent. Which means that for any polynomial f such that degree of f is strictly less than n, fa v is not equal to 0 for this v given, because otherwise we will have a equation equal to 0, and that implies that these vectors are linearly dependent. Yeah, so this implies that fa is not zero matrix. And so since for any polynomial that has degree less than n, fa is not 0, it means that the minimal polynomial, degree of minimal polynomial should be greater than or equal to n. But notice that the characteristic polynomial has degree n. So degree of minimal polynomial is exactly n. So this implies that the minimal polynomial equals to the characteristic polynomial, because it should divide the characteristic polynomial. Yeah. And that's the proof for this question.